This is the last subtopic under areas under curves. Under areas under curves. So we did integration. We had a look at these methods of approximation. And then volumes. Now, what's this about? If you recall, like the first 1 or 2 lessons when we were talking about integration, right? We said that the whole idea of integration was raised as a solution to area, right? So we've got this kind of notation. Yeah? Now, area equals, and then there are 3 parts to this, okay? There's that weirdo-looking S, there's this dx on the end, and then you either have like f of x or y or whatever in there. Now, just help me jog my memory, right? What do these 3 parts, what do they each signify? Let's start from the right-hand side. What is the dx? Where did that come from? It's the width of that little rectangle that we imagined, right? So we are taking area, and area has that dimension, and it also has, what's the y correspond to? Yeah, that's the height. And the tricky thing about it is that the height changes as you go to different parts of the curve, right? So that's why I don't just call it h, which is constant. I call it y, it's a function. The height's changing all the time, right? What was this bit on the front?
It's the starting and stopping point.
Yeah, okay, so I guess if you wanted to put one word on it, you'd call it kind of like the domain, right? It's like, where are we interested in all of these heights and widths and put them all together, okay? Now, having taken this idea, I said, look, when you do this summation, right, because it was from sigma notation, right? You take the sum of this thing, integration works, you can take the sum of anything. Do you remember what the example that I gave you was? Which wasn't just a rectangle. We took the sum of something else, a shape that you're familiar with. Do you remember? Yeah, we thought about circles. In particular, we thought about the surface area of a sphere. Remember that, right? And we looked at this result. We said, well, if we take the surface area of a sphere, which is what, 4 pi r squared, right? And the width of each one is, you know, dr, not dx, okay? And what was our domain? Where would we go from? Where would we start and finish? Do you remember? What's the smallest surface area of a shell that I would take? What would its radius be? 0, right? And then you go all the way up to r. We looked at that idea. Okay. I just want you to see the parallel between these two. Still the same summation, still something of infinite thinness, infinitesimally small width, anyway, right? But then what we put in here was drastically different. That's not a height at all. It's the area of a shell, right? So the idea is that you can use integrals to add up anything you like, so long as all the things that you've got are really, really tiny and you've got an infinite bunch of them. Now I'm going to take this idea that I can take the integral, I can integrate a whole bunch of anything I like, by thinking about, let's take a function, and I'm going to start with a simple one that you could find its volume in other ways, and seeing how I could muck around with it and use integration here. Okay. So if I had this function, okay, and let's say I was interested in the domain, let's go from 1 to 2, 3, 4, 5. Okay. So I could work out the area of this, well, it's a rectangle, but I could work it out by integration. Right? What integral would I form for this particular one? Okay. Integral of, what are my boundaries? 1 to 5, right? And what? 2. And I'm interested in this bounded with the x-axis. Okay? So that's going to give me an area. Okay? But here's what I want to do. Just like from here to here, I went from a height to, that's a shell, right? A surface area, okay? I'm interested in what would happen if I took all of these little rectangles, that's what this is, right? And each rectangle has height too, okay? So for instance, one little rectangle like that. And what if I make that rectangle the radius of a circle? Now where would the circle go? Okay. Now, being that I've got a whole bunch of these rectangles, rather than make the circle fit that way, the way we're looking at it, okay, I want you to imagine the circle going further into the wall and coming out, okay? So it kind of looks like this. Maybe I should do that sort of. Okay? So I've taken that, I've made it a radius, and now I've got a circle, okay? Now, what happens if I get a whole bunch of those? You know, I've got one here, and one here, and so on. what kind of shape am I going to get?
Cylinder.
This is a cylinder, right? Okay, now if you're having trouble visualizing this, okay, I'm gonna draw on a favor from some math teachers of the past, and I wanna reference them because they're long gone now, and they put this hard work in, and it's going to benefit you. So Mr. Howlett and Mrs. Cannon, you remember Mr. Howlett, but Mrs. Cannon is before your time. She was almost before my time, but I remember when she was around. So they put these together. Now, what is this? Well, it's a cylinder, okay, but how was it made is the important thing. You can see, if you want to think about it that way, rather than like shells, spherical shells, I have kind of like slices, right? And these are all the circles that have been made that I've put together, okay? And you put enough of them together and you get a solid shape. Hence a solid, okay? Now, what I'm interested in is integrating, putting together, combining all of these, and I should get a volume at the end. Okay? So you can see why it's called a solid of revolution. It was not so named because they were modern history fans, but it's by taking that radius, right? And this is important on your diagram. Get another color if you've got it. The way I make this cylinder is by taking that radius and revolving it around the x-axis. Okay? All right, now, how would I find, like we're already expecting that this is going to be a volume of some kind, okay? You put together a bunch of one-dimensional things and you'll get a two-dimensional measurement. You put together a bunch of two-dimensional things and you ought to get a three-dimensional thing, which is a volume, okay? Now my boundaries are still the same, I'm still going from 1 to 5, but instead of a 2, what's going to be in here? Now, instead of just like a line, right? What I've made is a circle, okay? But we know what the area of a circle is, right? What's the area of a circle? Pi r squared, right? Now, in this case, my radius is 4, okay? So I'm going to get pi times 2 squared, yeah? Is that okay?
Wait, you said your radius is 4.
Oh, did I? Sorry. Radius is 2, right? 2 squared is 4, and I need a width, right? I need a width, okay? So what am I going to get out of this? Well, let me just tidy this up. This is 1 to 5 of 4 pi dx. Okay, now, you tell me. Now, I could take a lot of things out. I'm just going to leave, for now, I'm going to leave them. Okay? What is the integral, what's the primitive function for 4 pi?
4 pi x.
It's just a constant, right? So here's what I've got. 4 pi x from 1 to 5. Okay, let's go ahead and evaluate it, right? What do I get? I'm going to get 20 pi minus 4 pi. Yes? So that's 16 pi. And of course, because I'm actually working out a volume, you can conclude this ought to be 16 pi units cubed, okay? Now here is why I chose this shape, because we know how to work out the volume of a cylinder, right? What's our regular formula for the volume of a cylinder? It's pi r squared h. This is my base, right? So it's a prism, just like any other. So what is it in this case? So what's my radius? It's 2. And what's my height? It's from 1 to 5 is 4, right? So it looks like it checks out, at least in this case. Okay. So can I generalize this a little bit? I mean, this is one specific example. Okay. Where was the crucial step that took us from I'm working out areas to working out volumes? What was different? The boundary was the same. Boundary was the same. The width of each item, the width of each of these slices, if you like, was the same. What was different was, what am I adding up? I'm adding up these shapes now. I'm not adding up these little rectangles. I'm adding up circles. Okay? So therefore, this is the crucial part here. Okay? Because in adding up circles, what I'm really adding up is pi r squared, right? A whole bunch of circle areas. Okay? So let's generalize this. Suppose it wasn't y equals 2. Okay? Suppose it was, whatever function you like. Okay? How would I find its area? Well, the volume is going to be, you pick wherever you want it to be. So from A to B. Okay? Now, because I'm adding up a bunch of circles, right? This is going to be pi r squared, but the radius will each time be y, whatever that height is. So instead of pi r squared, I'm going to have pi y squared. And then, of course, I've got the width of each of those slices, right? Now, as Richard noticed before, this pi is a constant, okay? So it makes sense to bring this out the front. So this is our expression for, and you want to put like a nice big box around this, okay? This is our expression for a solid of revolution, a volume that you get by taking a function and rotating it around a certain axis. In this case, it's the x-axis. That's what the dx signifies, okay? Just like before, the dx signifies an area bounded by the x-axis. This is a volume around the x-axis.